Every single time you skip a meal, your body quietly launches an emergency response most people never notice happening. Insulin, thyroid hormone, growth hormone, mitochondria, and fat cells argue constantly over how your energy gets spent. Do this once, and the effects vanish within hours, barely leaving a trace behind in your biology. But repeat it daily for 30 straight days, and something completely different starts happening inside your cells. Some of these changes have been measured in real human trials, while others only exist in mice. By the end of this, you will finally understand exactly where the real evidence line sits. Right after eating, your body flips into storage mode, prioritizing input over any form of output. Insulin rises sharply, pulling glucose into your cells while packing the leftover energy away as glycogen. Anything your muscles and liver cannot store gets quietly rerouted straight into stubborn long-term fat storage. This storage state is the default for most people, most hours, most days of their entire lives. Somewhere between 12 and 36 hours without food, your body crosses a hidden metabolic threshold. Researchers call this shift the metabolic switch, a slow closing valve rather than a sudden flip. Glucose availability drops steadily, while fat becomes fuel out of necessity, not personal preference. This is not the same thing as autophagy, even though people constantly confuse the two. The metabolic switch decides what your cells burn, while autophagy decides what gets cleaned out. They share triggers, like falling insulin and a rising energy sensor called AMPK activating together. But triggering one daily for 30 days does not guarantee the other follows at equal strength. That distinction becomes surprisingly important once we start talking about your mitochondria later on. The first few hours of fasting are almost boring, metabolically speaking, and barely register at all. Blood sugar stays steady because your liver breaks down stored glycogen through a process called glycogenolysis. That same glycogen reserve typically runs dry somewhere inside that 12 to 36 hour window. As glycogen drops, glucagon rises above insulin, unlocking fat cells to release their stored fatty acids. This release process is called lipolysis and feeds fatty acids straight into your bloodstream immediately. Once those fatty acids reach your liver, some get converted into ketones, an alternative brain fuel. This is the metabolic switch actually happening live, not theory, but a real chemical event. Do this once, and by your next meal, nearly everything reverses within a matter of hours. Do it daily for 30 days, though, and you are not repeating one long event. You are compressing dozens of short metabolic events, one after another, day after day, relentlessly. That repetition, not the single fast itself, is the real subject worth understanding here. Insulin sensitivity simply means how efficiently your cells respond when insulin knocks and asks for glucose. Poor sensitivity, known as insulin resistance, sits at the center of most metabolic dysfunction today. Researchers studied 8 healthy young men fasting 20 hours every other day for 15 days straight. Using the gold standard glucose clamp technique, they measured insulin sensitivity before and after this protocol. Glucose uptake improved measurably afterward, alongside a rise in adiponectin, a hormone supporting healthy insulin signaling. But this study ran 2 weeks, not 30 days, and used alternate day fasting, not daily fasting. Other human trials using similar methods found smaller effects, or sometimes no measurable improvement whatsoever. So the honest answer is repeated fasting improved insulin sensitivity within a 2 to 3 week window. Whether that improvement keeps climbing, plateaus, or reverses by day 30 remains completely unmeasured territory.
Mitochondria convert fuel into usable energy, and like everything else in your body, they wear down. Damaged mitochondria do not just work poorly, they leak reactive molecules that stress your entire cell. Clearing out these damaged units is called mitophagy, a specialized branch of the broader autophagy process. Meanwhile, a separate process called mitochondrial biogenesis builds brand new mitochondria to replace what was lost. Fasting activates AMPK, which then triggers a protein called PGC1 alpha to coordinate new mitochondrial construction. This pathway is well documented in animal studies, where fasting reliably boosts both mitophagy and biogenesis markers. Here is the honest caveat nobody wants to mention when selling you daily fasting as a miracle. A systematic review comparing rodents and humans found this dramatic mitochondrial response barely reproduces in humans. So when someone claims daily fasting rebuilds your mitochondria, they are usually citing strong rodent data. That rodent data sits layered over a thinner, far more contested picture inside actual human muscle tissue. Keep that gap in mind because it resurfaces again and again throughout the rest of this story. Your thyroid sets your baseline metabolic rate, mainly through two hormones, T4 and its active form, T3. Most circulating T3 is not made directly by your thyroid. It converts from T4 in peripheral tissue. That conversion step happens to be exactly where fasting leaves its clearest biological fingerprint every single time. In one study, 7 men and 7 women fasted 60 hours while researchers tracked their thyroid hormones. T3 dropped significantly in nearly every subject, falling between 24 and 55% from their baseline. Meanwhile, TSH, the signal telling your thyroid to ramp up, stayed essentially unchanged throughout the entire fast. Researchers traced this drop to reduced conversion of T4 into T3 in your peripheral tissues, not gland failure. This is not your thyroid breaking down, it is your body deliberately dialing back energy expenditure. It is conserving fuel on purpose, a survival strategy hardwired deep into your ancient biological programming. What that 60-hour study cannot tell you is what happens across 30 shorter fasting cycles. T3 might partially recover between each fast, rather than staying suppressed the entire month straight through. One long dial down and 30 short ones could behave completely differently, and nobody has compared them. Everyone knows fat gets burned while fasting, but the actual mechanics are far more fascinating than that. The classic route is lipolysis, where enzymes break triglycerides apart into fatty acids for other tissues to burn. But researchers using mouse liver cells discovered an entirely second pathway hiding beneath the surface all along. Lipid droplets get captured directly by autophagosomes and delivered to lysosomes, a process called macrolipophagy. In that same research, fasting increased both the frequency and the autophagy markers on these lipid droplets. In plain terms, autophagy is not just cleaning debris, it is actively pulling fat straight from storage. That fat then gets fed directly toward beta oxidation, the process that burns fatty acids for energy. But this mechanism was demonstrated in mouse liver cells, not inside any living human being yet. Follow-up research extended this finding to fat tissue itself, again strictly within mice, not humans. Human lipophagy is brutally hard to measure directly since it requires tools separating it from ordinary lipolysis. A human liver running this same process daily for 30 days is a plausible, unproven extension of mice. Growth hormone usually gets filed under muscle and height, but fasting reveals its hidden secondary role entirely. It acts as an amplifier for fat mobilization while actively protecting your muscle protein from being burned. Researchers measured hourly growth hormone in 7 men before and during a 72-hour fast. Secretion increased in every single subject, rising roughly 2.5 to 3 times normal levels. Growth hormone pushes fat cells to release more fatty acids while shifting tissue toward burning fat instead. This is part of why short fasts do not automatically translate into immediate dramatic muscle loss. What remains unclear is whether this growth hormone surge stays this dramatic across 30 repeated daily triggers, or whether your body starts moderating that response the same way it moderates other repeated hormonal exposures. The direction of the effect is well established, but the long-term repetition question stays completely unanswered. Researchers Kelly and Mandarino coined a term tying all of this together called metabolic flexibility. It describes your capacity to switch from burning fat while fasting to burning glucose once you eat again. A metabolically flexible person moves between these fuel states quickly, efficiently, almost effortlessly, without any friction. Someone metabolically inflexible gets stuck, often burning glucose while fasting and struggling to burn fat when needed. This matters clinically since insulin-resistant people consistently show this frustrating metabolic inflexibility in repeated studies. Flexibility is not abstract theory, it is a measurable marker tracking real fuel-handling health inside you. The same glycogen depletion, lipolysis, and insulin changes discussed earlier are exactly this fuel switching in action. If those daily shifts genuinely repeat for 30 days, your fuel switching machinery likely gets more practice. No published trial has directly measured metabolic flexibility before and after 30 consecutive days of daily fasting. The logic connecting these dots holds up perfectly, but the confirming data simply does not exist yet. Everything so far points toward positive adaptation, but metabolism does not always adapt in convenient directions. There is a well-documented phenomenon complicating this entire picture called adaptive thermogenesis, and it matters greatly. Researchers tracked energy expenditure as subjects lost 10 to 20% body weight under controlled hospital conditions. Energy expenditure dropped beyond what smaller body size alone would explain, actively working against keeping weight off. A randomized trial on time-restricted eating found participants lost minimal total weight over 3 entire months. Worse, they lost more muscle than fat, with lean mass making up an outsized share of total loss. This does not mean daily fasting always causes this outcome for every single person who tries it. Protein intake, training status, and how aggressive the fasting window is all heavily shape the final result. But it remains a real published human counterexample to the idea that fasting is a flawless upgrade. Combine this with thyroid suppression and uncertain human mitochondrial data, and a clear pattern starts emerging here. Several mechanisms that look purely beneficial in isolation are the exact same ones triggered during scarcity survival. Whether 30 days of daily fasting lands closer to benefit or conservation depends heavily on the individual. Baseline metabolic health, what you eat during your feeding window, and protocol intensity all shape the outcome. So let's pull this together into what actually rests on solid, repeated human evidence right now, today. Repeated fasting reliably triggers the fatty acid and ketone-based metabolic switch described earlier in detail. 2 to 3 weeks of alternate day fasting has, in controlled trials, improved insulin-mediated glucose uptake. A single extended fast reliably raises growth hormones several times over while increasing fat mobilization significantly. Thyroid hormone conversion slows measurably within days, a deliberate adjustment rather than any form of malfunction.
Other pieces remain genuinely open, unresolved, and honestly still waiting for someone to properly study them. The mitochondrial biogenesis story stays strong in rodents, while remaining noticeably thinner across human research studies. Lipophagy has strong mechanistic support in animal liver cells, but has never been measured across a human month. Adaptive thermogenesis means 30 days of daily fasting could just as easily produce slowdown as improvement, especially for anyone eating insufficient protein while pushing an aggressive, unforgiving daily fasting schedule too hard. There is no single published trial testing exactly 30 consecutive days of daily fasting in healthy humans.
What exists instead is a mosaic of short trials, longer single fasts, and detailed animal mechanisms combined. They point in a coherent direction without ever adding up to one definitive 30-day human dataset. That gap deserves honesty rather than convenient hype because it represents the real state of current science. Your metabolism is not broken, and it is not magically upgraded either. It is simply adapting constantly. Understanding where the evidence actually ends is more powerful than blindly trusting where the confidence begins.